Good afternoon and welcome to Orkney International Science Festival online. My name is Matt Vidmar and it is my pleasure to be hosting this special session of the first online edition of the Orkney International Science Festival. In this year, the festival is celebrating 30 years since its foundation, and it is great to see its first online version. Of course, some of that is to do with the COVID pandemic, but we're delighted to be able to bring the festival content to so many more people all around the world. This afternoon, I am joined by Professor Graham Machin, who is the head of temperature standard at the National Physics Laboratory, and is a world-leading expert in temperature measurement. He has published more than 220 papers and is a visiting professor at both the Strathclyde and Surrey universities. He was recently elected honorary scientist of the Chinese Academy of Sciences, and he's a fellow of the Royal Academy of Engineering. He's also director of the multinational project Realizing the Redefined Kelvin, and leads the NPL, so that's National Physics Laboratory's activity in nuclear decommissioning metrology. As the inaugural chair of Global Task Force on Improving Body Temperature Measurements, he leads the world team of experts in this field. Tonight's talk is going to discuss the art and science of temperature measurement, entitled, quite poetically, Mercury Rising, Measuring Temperature Through Time. And it's going to cover anything for the developments from the 17th century until the present day. In a second, I'll pass on to Graham to tell us all about metrology. But in the meantime, if you do have any questions, we are hoping to have a Q&A session after Graham's presentation. Please feel free to drop your questions in the discussion chat below the video. Now over to Graham to tell us all about Mercury and how it measures temperature.
Thanks very much, Matt. That was really great. Welcome to my presentation, which will appear very shortly. And thank you for attending. I'm very sorry not to be in Orkney in the flesh, as it were. Very beautiful place. I've been there many times before. So next slide, please. So I want to just say just a few words about where I work. I work at the National Physical Laboratory, which is based in southwest London in Teddington. That's where it is. This is a photograph of our campus, or one of our buildings on our campus. There's about 1,000 people work at the National Measurement Institute, the NPL. And we have branches in Scotland at Strathclyde and also in Northern England in Huddersfield as well. And I just want you to not to be confused about metrology and meteorology. Meteorology is the science of weather forecasting and all that sort of thing. Metrology is the science of measurement. So that's what we are talking about today. Next slide, please. So I really want to focus on what temperature is, and then go on to talk about temperature scales. I hope you don't find it too dry, but it should be, it's a very interesting subject, at least to me, it's very interesting. And I'm going to talk about what happened in the past and how de facto scales arose, and I'll explain what that means in a few moments. I want to talk about what it's like now in terms of measuring temperature, and then what might happen in the future in the next 20 years or so. Next, please. So first question is really, do you really know what temperature actually is? If you look at it in a dictionary, it says it's something you measure with a thermometer, which doesn't really tell you anything, does it? So what does temperature mean? Next. So there's a picture there. You can see a thermometer measuring temperature. But what does it mean? Next, please. So it's a very interesting and subtle concept. If you have, and you can really think how subtle it is when you work out the comparison with mass or with dimensional measurement. For instance, if you have 2 meter sticks and put them together, well, you have just 2 meters, don't you? Or if you have 2 kilograms, you have 1 kilogram and another kilogram, and add them together, you get 2 kilograms, don't you? But if you have 2 cups of water at 60 degrees Celsius and you add them together, what's the temperature of the water? Does it add together and does it become 120 degrees Celsius? Well, common sense tells you, of course, that it doesn't do that, because if you put 2 cups of water at 60 degrees Celsius together, they would boil if they went to 120, wouldn't they? And they don't do that. So there's something subtly different about temperature compared to mass or compared to dimensional measurement. So can you go on to the next slide, please? Sorry, next slide, sorry. Next slide, I've said that. So I want to really talk about the numbers on a thermometer. What do the numbers on the thermometer represent? What does temperature really mean? Does it have a physical meaning? Do those numbers on the thermometer have a physical meaning? What do they really tell us about the physical world in which we live? So I'll explain some of these things as we go along. So let's go on to the next slide with a trip to Florence in Italy. Next slide, please. So when you think of Florence, what comes to mind? Well, there's obviously the beautiful Uffizi art gallery full of the world's great art treasures. There's the beautiful cathedral, Santa Maria del Fiore, which, as you can see, there's a beautiful, beautiful place. And of course, there's Ponte Vecchio, the oldest multi-columned bridge anywhere in Europe. In 1340s, I think it was built. These are all very historic and beautiful places. And I happened to be in Florence last year with my wife, and she was very keen to go to the Uffizi Art Gallery, but actually I wanted to go somewhere else. Next slide, please. So we compromised and spent half a day in Uffizi, and half a day went to the important place, which was the Galileo Museum in Florence, which is a museum of the Institute of Museum of Science. And why is that so important? Why is that so interesting? Interesting to me, at least. Well, if you see the next slide, you'll see why. Because in that museum is actually one of the best collections of historic thermometers in the world. And I'm afraid my camera has lots and lots of photographs of the pictures of the historic thermometers that are there in that museum. I have a very long-suffering wife who came round and enjoyed looking at thermometers as well. Next slide, please. You can see here a very beautiful example of mid-1600s, late 1600s, of Florentine thermometry, really the peak of that technology at the time. You can see the dots, which are the scale markers made by the Academy of Science at that time. And this is calibrated at 2 fixed points. The fixed points of snow and the hottest day in Florence. Now, snow doesn't have a fixed temperature. It could be any temperature really below zero. And of course, the hottest day in Florence could be different from day to day. So they weren't very reliable fixed points, but at least they were trying to give a calibration at 2 fixed points. And that's just really one of many different scales that were emerging around that time. Next slide, please. So welcome to the 17th century, where de facto scales were emerging. Next slide. Briefly, right, next slide. So in the 17, 18 centuries, thermometers were made like that. You've seen them. They were liquid in glass, often alcohol, but as the century progressed, mercury was increasingly loose, particularly in the 18th century. And there were a very large number of temperature scales began to be in use. Next slide, please. So for instance, here's a nice slide of a picture I took in the Museum of History of Science in Oxford. They have this Royal Society thermometer from the early 1700s, and it's got an inverted scale. So on the right-hand side, if you can see it, if I'm not blocking your view too much, you can see that the very highest temperature is at 0 degrees of this scale. And then as you go down in temperature, the actual numbers increase until you get to the freezing point of water, which is 65 degrees in this scale. So it's an inverted scale. Next slide, please. Here's a thermometer that has quite a wide number of scales. I'm afraid I can't see at the bottom of the thing, but I think it says 15 scales. This is from the University of Utrecht Museum in the Netherlands. And you can see there's a wide variety of scales there. Next slide, please. And then by the time it got to the time of approximately the French Revolution, things were a bit silly, really, weren't they? And this is a conversion table in a book from the library in Paris, and there are 28 different scales in use, and there were probably many more that didn't make it into this calibration table. So it's a very complicated thing. So if you think about weather forecasting, for instance, and temperature records that went back to this time, to even know what scale was being used and trying to incorporate any data that is taken at that time is quite a monumental task, in fact. Next slide. So those scales were based they were really arbitrary. They were based on fixed points whose temperatures were fixed by convention only. So typical fixed points that were used were the freezing or the boiling point of water, or human body temperature is another common one. But there were more unusual ones, like we saw the one in the Florence one, didn't we? The melting point, sorry, the temperature of snow, or the hottest day in Florence. Here's another one, the melting point of butter is another one, or the temperature of a very deep cellar under the Paris Observatory. So there's a wide range of different fixed points that were used. But by the beginning of the 19th century, there were three main ones in use in Europe, certainly. So you go to the next slide and I'll talk about each one. So the first one was by Fahrenheit. I guess all of you have heard of Fahrenheit, still in common use by our American friends. He used mercury thermometers, and his scale had three fixed points, and you can read about them in the Royal Society Philosophical Transactions. He used human body temperature as the upper point of 96 degrees Fahrenheit. He had an intermediate temperature point, the mixture of ice and water, 32 degrees Fahrenheit. And then the lower point was a mixture of brine, was a solution of brine, sorry, with ice, water, and salt at 0 degrees. But actually, in practice, that wasn't really ever used. And today, the water freezing point and boiling point are the ones that are used to define the scale. Next slide, please. And then here's another scale widely used in Europe by René-Antoine Réaumur. He proposed his scale in 1731, and he used alcohol in his thermometer to begin with. And his proposal was a bit strange to follow. The first part was easy. He had one fixed point as the freezing point of water, but the other fixed point, as you can read here, was very complicated. An evaluation of the expansivity of the thermoelectric fluid up to when it just stopped boiling at a point which he says it was convenient, 80 degrees, convenient for dividing into parts. And his definition was so difficult to understand that most people didn't understand it. And they just really thought, oh, he must mean that 80 degrees Réaumur is the boiling point of water, which isn't actually what he meant. Next slide, please. So everyone believed that, and that's what became established. And so the temperature scale, using Réaumur's ideas, set the freezing point of water at 0 degrees and the boiling point of water at 80 degrees. And this was widely in use in the 18th and the 19th century in Europe. Next slide, please. I'm making a distinction here between Europe and the UK here, because, of course, the UK wasn't part of the EU then or anything like that. And the UK had quite a different scale, and you'll see that. Now, the Swedish thermometer, Swedish astronomer Anders Celsius, also had his own scale as well. He used mercury from the beginning, and he had an inverted scale. The melting point of ice was 100 degrees centigrade, and the boiling point of water was 0 degrees centigrade on his scale. So you can see it was inverted. And the botanist Linnaeus, who was a very famous botanist, reversed that scale order, and it was used afterwards like that, but it's still named after Anders Celsius. So next slide, please. So here's a picture of an old thermometer, and you can see here this has got the Fahrenheit scale on one side, on the left-hand side, and the Réaumur scale on the right-hand side. As you can see, 212 at the boiling point of water and 80 degrees Réaumur as the boiling point of water as well. Next slide. But by the beginning of the 19th century, these three scales, as I say, were the ones that were mainly in use: the Réaumur scale, the centigrade scale, and the Fahrenheit scale. And in mainland Europe, the Réaumur scale was very popular, and the centigrade scale grew in popularity. And in the UK and in the US, the Fahrenheit scale was very much in use. Next slide, please. Just want to show you this little barometer. This is my barometer, and hanging on my wall in my study up here. Now I can see it, and it's nice because it has thermometers. Don't do this to your thermometers at home, by the way. It won't do them any good. But it has thermometers which measure the three different temperatures: Fahrenheit, centigrade, and Réaumur. So it was made in about 1870. And they've used mercury, which is the better liquid, for the Fahrenheit scale, because that's the English scale, as it said, as it was then colloquially known then. And they've used alcohol for the centigrade and the Réaumur scale. But actually, I've checked the calibration of the centigrade thermometer as one would where I work, and actually it's still within 1 degree of what the true temperature is. So that's pretty good for a thermometer that's 150 years old. Next slide, please. So, as I said, all these scales are based really on arbitrary values of fixed points. The thermometers themselves, though, actually became better and better as time went by, because standards in manufacturing improved and became standardized. And the temperatures that the thermometers gave became more reproducible. But again, the temperatures, as I said, had no physical significance at that time. So next slide. So I want to really then think about, what does temperature mean, and the emergence of primary thermometry going on to define temperature scales, which give temperatures which have a real physical meaning. Next slide. So primary thermometer, I'm sorry you can't see the picture on the right-hand side. That's a simple gas thermometer by Amintons. So basic primary thermometers and some of the principles were already known by the 16th century, 17th century. So for instance, Boyle's law, that the pressure times a volume equals a constant at a constant temperature. That was a well-established principle by the 17th century. Next slide, please. But it wasn't until this book, this famous book in thermodynamics, it wasn't really thermodynamics, in hydrodynamics, by Daniel Bernoulli, was published in 1738. And in that book, he asserts that gases consist of a great number of particles moving in all directions, small particles, whose impact on the surface causes gas pressure. And this was pretty shocking. And actually, most scientists didn't accept that couldn't be possibly true. Scientists didn't believe that those sorts of things existed. Nevertheless, very famous people like James Clerk Maxwell, building on the work of Rudolf Clausius, did some very clever mathematics and established the basis for what's known as statistical thermodynamics, making the assumption, because no one had really proved it at those times, that yes, Bernoulli's assertion was right. Yes, gases were made of large numbers of particles moving at different speeds, and he formulated the foundation of statistical thermodynamics and derived a number of equations which actually showed or inferred at least, that Bernoulli's assertion was correct. Boltzmann then built on that work and generalized it. But all this work was being done when people thought that those particles were just theoretical constructs and didn't really exist. Not most scientists didn't believe it. And it was only when people like Einstein and did some analysis of Brownian motion, for instance, that particles started to believe to be real entities. Next slide, please. The other aspect of thermodynamics and thermometry was Lord Kelvin's analysis of heat engines, and his collaboration with James Joule was really seminal in this. And his work on temperature measurement and efficiency of heat engines led to two key developments, which led to the fundamental understanding of temperature. One was that there's an absolute temperature, that is a temperature that's independent of substance, whether you're measuring wood or gas, or whether you're measuring a liquid, the temperatures in those is independent of those things. And in particular, the idea of absolute zero as well, when particles come to rest, when there is no motion. So next slide, please. So when these ideas came together, the thermodynamics, the statistical thermodynamics, and those ideas of Kelvin came together, we get an idea of what temperature really means. As we now know, of course, that matter is made of atoms, and in a gas, those particles, and if it's a monotonic gas, those atoms are unbound. They have a wide range of speeds, and an associated kinetic energy, and the whole ensemble has an average kinetic energy. You know this when as atoms cool, they slow down, they have less kinetic energy, and they exert less pressure. So the temperature is just a very convenient way of expressing the average kinetic energy of the particles, and there's a direct relationship between T, the thermodynamic temperature, the absolute temperature of the gas particles, and the average kinetic energy of the gas particles in that system. Next slide, please. So this is a picture of the current NPL primary gas thermometer. If you saw my talk last year, you'll have seen a picture of this. It's the world's most accurate thermometer. It has exquisitely low uncertainties. I'm sorry, I'll switch to Kelvin now. Kelvin is absolute or thermodynamic temperature, and it measures temperature by measuring the speed of sound in a known volume, in a known gas. Next slide, please. But of course, it's a very impractical thermometer. It takes about 1 week to make a measurement. It requires a laboratory full of apparatus to do the measurement. It requires very expert research scientists, more than one really, to take the measurements and interpret the data. So this is certainly not a practical thermometer. Next slide, please. So just to summarize that then, what is the driver then? There are some drivers. So by the middle of the 19th century, when industrialization was in full swing, certainly in the western part of the world, there was growing requirement in science and industry for reliable and realistic thermometry. The ideal would have been to have practical thermometers that measured those thermodynamic temperatures that Kelvin had found in his analysis. So primary thermometry was really realistic and represented reality, but it wasn't practical, as you can see even now. One of the founders of reliable practical temperature scales, Hugh Longbourn Callender, said it's impossible for those who have never worked with the gas thermometer to realize the extent of its shortcomings. He's saying gas thermometry is very difficult. On the other hand, of course, so primary thermometry is realistic but not practical. De facto scales were practical, but they were not fundamental. So there's a circle there that needs to be squared, and I'll explain how that's done now. Next slide. What happens is that defined scales based on thermodynamic temperature of a number of fixed points emerged. So fixed points, I'll talk about what those are in a few moments. Freezing point of water is one. Their temperatures was determined using primary thermometers, so they knew what the thermodynamic absolute temperatures were of those fixed points. And then knowing those temperatures, they could then calibrate practical thermometers against those fixed points, and so establish a temperature scale that was very close to the primary measurements. And that was a really neat idea that happened at the end of the 19th century. Next slide, please. Okay, next slide. I've talked about that. So let's talk about what fixed points are. Next slide. So here's an example. If you did my talk last year, I brought a triple point water along for you to have a look at. Triple point is a very elegant fixed point because it's a unique point in its phase diagram where, and it's the only point in the phase diagram of a pure material where all three phases of the substance coexist: ice, water, and vapor. And of course, for water, that triple point is 0.01 degrees Celsius or 273.16 Kelvin. And that's that unique point on the phase diagram. Next slide, please. So we're going to run through the freezing point of a metal now. So just press next slide and we'll just see what happens. Next slide. So there's an ingot, a slice through an ingot of metal you can see in the furnace. Next slide. You heat the furnace up, keep going. You insert the thermometer, keep going. Let's just look at here. So here you see, next slide, next. The metal melts. We allow the metal to cool. You can see it cooling. There's an undercool. You also get an undercool in a very pure substance. And then you see the fixed point stabilizes at the freezing point. Now that plateau is caused by the metal giving out the latent heat of freezing. And while it's giving out that heat, it stays stable at that temperature. And that point is then used to calibrate a thermometer. So the R on the scale is equivalent to resistance of the thermometer. Next slide. Okay, next slide. I won't talk about that. So Callendar, I mentioned him a few moments ago, really did the pioneer work with platinum wire. And he showed that the electrical resistance of platinum was a very practical and convenient way of comparing and hence disseminating sending out scales. All you need is a thermometer which is based on the resistance of platinum and a number of fixed points of known temperature, and you can set up a temperature scale. And his idea of doing that has formed the basis of temperature scales for the last 120, 130 years. Next slide, please. So the first true temperature scale was in 1927, and it has these three ranges. You can see Callender's platinum resistance thermometer was really the foundation from minus 190 degrees Celsius to the freezing point of aluminium at 660 degrees Celsius. And then a thermocouple, which is really just a very simple device. It's two wires of metal of dissimilar composition, and they're joined at a measurement junction, and they're put in a temperature gradient, and they generate a voltage, and that voltage is related to the temperature of the thing they're measuring. And so a type S thermocouple, which is a platinum rhodium alloy thermocouple, covered the range from the aluminium point to the freezing point of gold. And then measuring the optical emitted radiation was used above that temperature. I'm not going to talk about how that's done today. Next slide, please. These scales have undergone revisions and got better each time. In 1948, better fixed point values were used. So there's adjustment in the range and values. The water trip point was introduced. In 1968, there was a major extension down to very low temperatures, 0.5 Kelvin above absolute zero. And then the current scales in use around the world are the ITS 90, which I'll talk a little bit more about in a few moments, and the provisional low temp scale of 2000, which operates at very low temperatures from 1 Kelvin down to 0.0009 Kelvin above absolute zero, so very low temperatures indeed. And what's happened at each time is that the temperature that the scale realizes, so T90, for instance, is an ITS 90 temperature, has got closer to the true thermodynamic temperature. So that now, over, for instance, a wide range of the scale, the true temperature, T, difference from the temperature the scale gives, T90, is less than 20 millikelvin. In principle, you could make that better by having a new scale, but there's no plans for that at the moment. If you're interested, there's a website there where you can find out all about the history of temperature scales. Next slide, please. Next slide, please. So let's just say a few words about the current temperature scale. Next slide. So the current temperature scale has been in place since January 1990. I had the privilege of joining NPL less than about a year after it was set up. And my first job at NPL was to set up the temperature scale above the freezing point of silver, which was very interesting, as that had not been done in the UK before. The scale ranges all the way from 0.65 Kelvin above absolute zero, all the way up to the highest temperatures that can be measured. And you can see here that there's a publication where you can get a lot of information about the International Temperature Scale of 1990. Next slide, please. And the purpose of the scale is really it's just really like a recipe book. You have a recipe book to make food, to make meals, make cakes or whatever. So the ITS 90 is basically a recipe book. It's really a set of procedures, and you really follow the procedures, and you can set up a scale, which is a temperature scale, which is very close to the thermodynamic temperatures, but it is very precise and very reproducible. You can see in the right-hand corner the sensing head of a platinum resistance thermometer. This is a very precise instrument. They cost between £1,000 and £3,000 each. And you can see the actual coil of very fine platinum going into a furnace where the fixed point is. And on the bottom left, you can see a slice through this is a slice through an ingot of pure tin that was used for calibrating fixed points. Next slide, please. Here you can see the different fixed points that are used in the ITS 90. Don't be too put off by them. I'll just so on the left-hand side is the actual name of the fixed point. And then there's the temperature in Kelvin, the temperature in degrees Celsius, the uncertainty in the thermodynamic realization. That's how far away it is from true thermodynamic temperature. And then the uncertainty in the realization, which is actually slightly smaller. So for instance, if you look at the triple point of neon, which is the fourth item down in the list, the thermodynamic temperature is 24.5561 Kelvin, and it has a thermodynamic uncertainty of 0.5 Kelvin. For instance, that's how to read the table. Next slide, please. So the foundation of current scales is just as it was when it was set up in 1927. There are fixed points whose thermodynamic temperature was assessed by primary thermometry, and then they're used to calibrate practical thermometers, which are then used to disseminate the scale out to users. So that's really still in use today. Next slide, please. I thought this would be nice to see what's possible. So this is just a routine freeze of an indium metal fixed point. So you remember the ingot you saw in the previous couple of slides. Well, this is one that's got indium in. You can see here the scale division is 1 millikelvin. That's 0.001 degrees Celsius. And you can see that within the central portion between 2 and 8 hours, sorry, that the actual plateau, the freezing plateau, is about 0.2 millikelvin. Exquisitely good way of reproducing temperature. So that's just to show what current technology is available. Next slide, please. Okay, so what's going to happen next? So that's the state we are today. Are those defined scales ever going to be superseded? Well, let's see. Next slide. And I think that it could possibly happen. Now, again, last year I spoke a lot about the redefinition of the SI, so I don't want to spend much about it here. But really, the redefinition of the SI has galvanized the temperature community into looking at practical primary thermometry. So the SI, the International System of Units, which is the units that are in use around the world, were redefined, or there was a vote to redefine them on the 16th of November 2018 in Paris, in Versailles. Next slide, please. And then it became implemented on the 20th of May. And I had the privilege of being at the vote to implement the redefinition. Next slide, please. So let's just step through this. So I'll say next until we get to the end. So next, 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 next. Okay, so stop there. So before the redefinition happened, the SI units were based on a range of things. There's one artifact, the kilogram. There's a number of atomic or material properties, the Kelvin being one of them, and its triple point. And then there was some fundamental and conventional constants. That was the previous SI. And the idea is to remove the artifact and try and remove conventional constants and base everything on fundamental constants. So next slide, please. Let's step through here. Next slide. I'll just say next until you stop. Next, 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 next. Okay, fine. Oh, one more, next. Okay, so here, what's happened now is that the International System of Units is artifact free. The kilogram has been removed. The water triple point, which is a quasi artifact, has also been removed. And the SI is now based on a range of constants. There are there are 5 constants that are the foundation of the SI: an atomic property, the hyperfine structure of cesium, and there's just one conventional constant used for optical radiation. So the SI units are now artifact free. Next slide, please. So this is the old definition of the Kelvin on the triple point of water. Next slide. The new definition is based on a fixed value of the Boltzmann constant. It just makes explicit what's hidden in the triple point definition. What's explicit here is that the Boltzmann constant is the mediating constant between temperature and energy. And so it's joules per Kelvin. And so it's just really made explicit that temperature is really all about kinetic energy. Next slide, please. So why is there a need for practical primary thermometry? Why not just continue with defined scales? Well, in one sense that you could do that, but if you could make practical primary temperature sensors, that has very important benefits. All temperature sensing use at the moment drift over time, and they require periodic calibration if they are to remain reliable. Now, temperature sensor drift has a lot of important implications. In industrial process control, it can lead to more energy being used than needed. It can lead to greater emissions than there ought to be. And it can actually lead to poor product being produced, which has to be turned into scrap. So poor temperature control is very bad for industry. It can lead to unreliable results in scientific research as well if you don't keep your thermometers well calibrated. And it can also lead to less reliable medical diagnosis. And this is one of the things I've been working a lot on in the last sort of 9 months or so on body temperature measurement. What's the implication of if you miss a fever for spreading COVID-19, for instance? So that's a whole different talk to talk about medical thermometry, which maybe I'll do another time. But if you have primary thermometers that are directly linked to the redefined Kelvin based on fundamental physics, then the temperature they give will always be right, and temperature measurement will be revolutionized. Next slide, please. So here's just a few examples. Factories periodically need to calibrate their sensors or replace them. Well, you wouldn't need to do that anymore. If you had primary sensors, you could just run the factories and the sensors would always be right. That would be a really great win. Or if you have a very hazardous environment where you can't change a thermometer, like inside a nuclear reactor or a nuclear waste store, where you need a thermometer to be accurate for 50 years or 100 years or maybe even longer. Well, if you have a practical primary thermometer, again, you can measure temperature without having to worry about calibrating the sensor. Or global temperature monitoring, I hinted about it before with the changes in scales. You have to keep making adjustments for those scale changes. If you use practical primary thermometry, you wouldn't need to make those adjustments anymore. You'd be measuring true temperature right away. Next slide, please. So those primary scales would be set, those primary sensors would be set up. There'd be no need for calibration. It'd be a direct use of the redefined Kelvin. So actually, we've just really begun a new journey in temperature measurement and also mass measurement as well. And we're just taking the first tentative steps in the Realizing the Redefined Kelvin project. You can go to the website and have a look at it there. It's a bit slowed down because of COVID-19, but we're making some good steps. Next slide, please. So really come to the end of my talk. I've just got a few words to say in the end. You can see we've come from a very long way to really no understanding of the physics, to de facto scales based on arbitrary scales, arbitrary temperatures of fixed points, through to defined scales, which gave you reliable temperatures, which increasingly over time became closer and closer to thermodynamic values. And ultimately, I think this will give way to primary thermometry, which is practical, leading to a demise in the defined temperature scales and the use of practical primary thermometers in a wide range of sectors. Next slide, please. And of course, you all thought measuring temperature was easy. How can you talk about it for 40 minutes? Well, I can talk about it for a lot longer as well. I've only really scratched the surface, haven't I? Next slide. I've written a book chapter in this book by my colleagues, by Jim Grozier, Cooper, called Precise Dimensions. It was a very interesting meeting on measurement, and you'll find more details of my talk there. And I've also written a couple of articles about the redefinition of the Kelvin as well, if you're interested. Next slide. If you're interested in doing measurements at home, NPL has a website called measurements@npl.co.uk/MAH, measurements at home. And if I hope it never happens again, but if we get locked down and you have children at home, or even if you're interested yourself, there's some interesting experiments you can do at home as well. So next slide. And that's the end of my talk. So any questions?
Hello. So thank you so much, Graham. That was fascinating. I've learned a lot. I'm a physicist by training, but I was struggling to keep up at some places because there's quite a lot, of course, as you say, art and science involved to making all of this work. And we did receive quite a few questions through our YouTube chat, probably more than we'll be able to get through in the next 10 minutes or so, actually.
Okay.
There's a couple of, so you've covered quite a lot of ground, starting from sort of the metrology, and sometimes I sort of mispronounce. I mean, I know very well the difference between meteorology and metrology, but sometimes I seem to mispronounce the word. But in any case, you cover quite a lot of the sort of ground in terms of the past tools and techniques. And we had some very interesting questions about that. So first of all, one of the kind of interesting questions is that we sort of have some idea of temperature records from the era when you've sort of mentioned sort of 15th, 16th century. How confident are we that we're actually able to accurately translate those records into modern day measurements, because they were using such different tools and different scales?
I think it's actually quite variable. I think as long as you know what the scale was that was being used, then there are conversion factors. You saw the table of conversions.
Yep.
There are conversion factors between the previous scales and the current scales. So I think that's known. What's less well known is how big the uncertainties are of those temperatures. They could be, although you have a thermometer, because the actual arbitrary fixed points that we use to calibrate it, each thermometer might be very different. Even though it had nominally the same scale, it could be several degrees different. So to actually get conversions to temperatures reliably is quite challenging, I think.
Yeah, so even
until the mid 18th century, probably.
So that error is as often in physics, that error is really where it starts to be interesting. You can have the nominal value, but of course the error is really where that can diverge quite significantly. Well, speaking of different temperature scales and conversion between them, we have a quite interesting question. Was there any particular, let's say, differences between different trades into which scales were used? Let's say, I don't know, the brewers who wanted to measure their temperature for a particular reason use a particular kind of scale and sort of swore by it, and also kept it as a trade secret, if you like.
Yes, that's a very, very good question. Yes, different trades did use different temperature scales. Particularly interesting one actually was one in the potteries, where Josiah Wedgwood had his own scale for measuring temperatures of firing his furnaces and making sure the pottery was made correctly. And actually, interestingly, if you ever go to Florence, there's a really interesting set of Wedgwood thermometers in the museum there. And then, of course, the iron and steel, although they had the same nominal scale, they also used all sorts of interesting things. Like a foundry man would often have a favorite piece of orange peel, which had the same color as the piece of metal that he was going to forge. And when the color of the orange peel matched the piece of metal, he knew it was time to forge it. And things like that were used.
Excellent. So again, speaking of the materials used to effectively make thermometers of one way or another, you've mentioned at some point, and we had a similar sort of question, that mercury proved to be the better liquid. Any particular reason why that is so? And I think I can guess a little bit, but I mean, I'm sure there's a proper scientific explanation.
Yeah. It just has a very linear expansivity.
Yeah.
I mean, if you think of water, water's maximum density is at 4 degrees. So actually, if you had a column of water, as the temperature went up between 0 and 4 degrees, the column would go down because of the maximum density. Then it would go up again. And alcohol has quite a variable density between 0 and 80 degrees or so. So that's the reason why mercury has a very linear expansion.
Yeah. Now, whilst of course, in terms of primary temperature measurement, we'd quite like to have as accurate and as detailed understanding of the phenomena as possible. In common use, Celsius and this alcohol-based thermometers are usually is still quite the most common ones. Do you see a particular reason why that might change in the future, and maybe more of the everyday use might switch towards kind of standards like Kelvin?
Oh, everyday use, I can't see it. I would have thought people would still use degrees Celsius or even
Because
degrees
it's,
Fahrenheit.
it's a useful, yes, indeed. It's a
It's just,
useful, because it's calibrated against water and, things that are actually happening in everyday life. So I suppose that kind of makes it very useful, right?
it's just very convenient, isn't it? But industry don't use liquid and glass thermometers anymore. They use electronic-based thermometers.
Yes. Well, we also had the sort of almost obligatory quantum questions, right? I mean, is there any way to improve on the measurement of temperature using quantum? And of course, you've just explained that the SI units have now moved to a standard defined unit. So it's more about how do you produce, I suppose, the primary thermometer to be as exact as possible. Is there a quantum effect that you might be targeting?
Yeah, more than one. We have that's another project and another time, but we're working on. I'm just working on a project looking at nano fabricated microresonators, both photonic ones which use optical resonances, and also micromechanical ones which actually has vibrating quantum vibrating strings in them, for instance, and you can use that as well for temperature measurement.
Excellent. I'm afraid we'll have to invite you back next year to explain more about all of those, right? Because there's probably way too much detail there to go into everything right now. Which basically brings me to the end of this talk. It's already gone 4:15. Thank you so much, Graham, for really, really exciting and very insightful presentation. And thank you to our audience at home, whether near Orkney or far away. We hope you'll join us for more Science Festival events. We're running, of course, until next Wednesday. The next talk is already later on this afternoon at 5 o'clock. There'll be a talk about the seas around Svalbard, all the details for which you can find at the Orkney Science Festival website. And there's also still spaces available for our evening festival club events, including the one tonight. So links of that will appear in the description below, as well as again on the Orkney International Science Festival website. And we are running the PD Kirk lunches, which are sort of, again, more informal events during lunchtime. The next one is, of course, tomorrow. Links, again, will appear both in the description below, as well as in the Orkney International Science Festival website. So I hope you really all enjoyed this event. Do feel free to like us on our Facebook page and follow our YouTube channel. But for now, thank you very much, Graham. Thank you very much, our audience, and have a lovely evening. Goodbye.
Bye.